This is section 5.8, and in this section we're going to be comparing some different modeling types, particularly the types that have constant rates of change, the linear and exponential ones. We'll do a little comparing and contrasting there, just to make sure we're all really clear on the similarities and differences. So first of all, the algebraic forms. We know that a linear function typically looks like mx plus b. F of x or y equals mx plus b. And an exponential function? A times b to the x. We did see that we can use e as a base, but we'll stick with the a times b to the x for now. All right, where those constant rates of change really come out is when you make tables of values for these functions. If I make a table of values, excuse me, for a linear function, and my x values increase by 1, then I know the y values will change by the value of the slope. Now the slope may be positive or negative, so this might either increase or decrease, but we're going to have that constant additive rate of change. We call that a constant absolute. Rate of change. By comparison, my exponential function, if I make a table of values for an exponential function and continue to have the x values increase by 1, instead of having the same thing added to the y's, for an exponential function, we're going to have everything multiplied by whatever the base is. Okay. That constant multiplier results in a constant relative rate of change. We think about that as percent. Okay. So linear, we're adding the same thing to y all the time, and we may be adding a negative number. Exponential, we're multiplying we're multiplying y by the same thing every time. And again, b might be fractional, right? It's possible for that to be decreasing as well. All right, graphically, these guys are pretty easy to recognize. A linear function with a positive rate of change or positive slope looks like that. And a linear function with a negative rate of change or a negative slope would just go be a downhill line. With exponential functions, we get our increasing and decreasing based on exponential growth versus exponential decay. So we get our exponential growth when our base is larger than 1, and we get our exponential decay when the base is smaller than 1. Notice, however, that in both cases, the graph either increases all the time, like these two, or decreases all the time, like those two. Both linear and exponential functions are either increasing or decreasing. There's never a mixture within the same graph or within the same function. All right, and the rate of change is m. And here the rate of change we can calculate from b. All right, that was my quick little overview. Let's take a look at some problems. In each case, we've got a table of values, and we'd like to decide whether we have a linear function, an exponential function, or actually, I think possibly neither one, although these might all be one or the other. And then we're supposed to find that equation for that linear or exponential function by hand. So looking at the first one, I see that the x's do go up by 1. So that means that the pattern in the y values will tell me something. And I'm looking at this, it's not adding the same thing for sure. I'm thinking it might be multiplying. multiply by 3, maybe. Let's just double check it. I start with the 5, multiply by 3 is 15, times 3 is 45, times 3 is 135, and then the 405. So that looks good. The pattern in the y values, multiply by 3. All right, so as soon as I know that it's a constant multiplier, that's a relative rate of change, that's an exponential function. Y equals AB to the x. Now I actually know the B already. The B is the constant multiplier, right? So in this case, B is 3. But I need to figure out the A value, and there are a couple of different ways of doing that. I'm going to show you kind of the equation method first. This should look real familiar to you, and then we can talk about another way of predicting without actually going into the equation. So if I want to actually do it from the equation, what I could do is say, well, I already know that B is 3. And then I could just take any point from this table and plug it in. So any point doesn't really make any difference. I'm going to use the first one. So 5 equals A times 3 squared. That says 5 equals 9A. So A is 5/9. And so I've got my equation, y equals A, which we now know is 5/9, times B, which is 3, to the x power. By the way, if you'd rather not mess with the equation, I mean, it doesn't take that much work, but if you really prefer not to, you can also use the pattern to kind of predict your way backwards through the chart, right? What I really need to know to find A is what happens when x is 0. So I need to go back to 1 and then to 0. If I am multiplying by 3 going down, it would make sense that I would have to divide by 3 going up. So if I take that 5 and divide it by 3, in fraction form I get 5/3. That's for x equals 1. I have to do it again to get 0. So divide that by 3. And in fraction form, I'd have 5/9. So there's that same 5/9 that we found using a little equation done with sort of a predictive method. You can do either one, whatever makes you comfortable. I'm just going to say that I would like to see the work either way. So I'd like to either see the little equation, or I'd like to see you kind of making those predictions, working your way back to the y-intercept to get the A value. All right, let's look at this next example. Once again, I'm verifying that yes, my x's go up by 1s. So I can use this table to predict what's going on. And I want to think about the pattern in the y values. This one looks like we're subtracting 4 or adding a -4. So that's not multiplication, that's addition subtraction. This one's linear. Great. If we have a constant multiplier, it's exponential. If we're adding or subtracting the same thing, it's linear. So y equals mx plus b. This rate of change right here is my slope. So m is -4 here. And so I already know y would be -4x plus b. And we now have the same two options as we did before. We could either kind of predict our way backwards to get to that y-intercept and find the b, or we can use the equation. I'm going to predict first this time. I need to predict back to 1 and then to 0. And if we're subtracting 4 going this way, we'd have to add 4 going that way. So 13 plus 4 would be 17, and 17 plus 4 would be 21. So I believe we're going to find that that B value is going to be 21. Let's look at it using an equation method as well. Again, you can pick any point you want. Oh, maybe I'll go for the middle this time. I'm going to go for that one. Y is 5 when x is 4. So 5 equals negative 16 plus b. And when I add the 16, I can say I do indeed get that 21 for b that way as well. So again, 100% your call which way you want to go about calculating that. And my equation ends up being, let's see, m was negative 4x plus 21. All right, we have a couple more. Looking at this one, again, I just double check it. I always got to verify that my x's go up by 1. Otherwise, the pattern in the table doesn't help me at all. But it does, so we're good here. And it looks like we are adding 30 each time here. So let's see. Adding or subtracting, that's a linear function. Y equals mx plus b. And we're adding 30 each time. So that's my slope. All right, so I now know y is 30x plus b. And once again, we can either predict backwards or we can solve an equation. This one has a ways to go to get back to the 0. I think I'm just going to use the equation method this time. And I'm going to put in the very first point. Doesn't matter which one you pick, though. 40 for y, 3 for x. So 40 equals 90 plus b. And subtracting the 90 is going to give me negative 50 for my b value. And so my equation is y equals 30x minus 50. All right, I've got one more. Again, x's are going up by 1, so I am good to go to use the pattern from the table. And I have to figure out the pattern in the y's. Definitely not subtracting the same thing every time. So I'm thinking multiplication. And probably the first thing you're going to see here is it looks like division by 10, right? Dividing by 10 is the same thing as multiplying by 1/10. So anytime you see division, turn it into multiplication by the reciprocal. Since we do have a multiplicative pattern in the y's, this one is exponential. Y equals AB to the x. Since I already know that relative rate of change, I already know that 1/10 is going to be my b value. So I'll plug that in right away. Y equals a times 1/10 to the x. Let's see, I'm going to go ahead and use the predictive method this time. Because if I'm multiplying by 1/10 this way, I would simply multiply by 10 over 1, or just 10, to go that way. So 1,000 times 10 would be 10,000. And 10,000 times 10 would be 100,000. So A is 100,000. And I'll leave it to you if you would like to try the equation method. Of course, that works as well. All right, on the next page, we have two more examples, and this time just instead of giving you tables of values, I gave you the graphs instead, but same question. Are they linear or exponential, and can we find the equations? And as I look at this, yes, this definitely looks exponential. Exponential decay, right? And I'm going to recommend, because it is so helpful to have that table of values to see the rate of change, I'm going to recommend that we just kind of make ourselves a little rate of change based on, or excuse me, a little table based on this graph. So let's see. It looks like x equals 0, y is 4. 1, 2. 2, 1. And after that, I would have to start guessing at fractions, and I don't really want to do that. But this should be enough, given that I can already see the exponential curve. This should be enough for me to identify my A and my B. So I know it's going to be y equals AB to the x. And I have the A value right here, the y-intercept. And then I'm going to notice that I did, thank goodness, pick x values that went up by 1, meaning I can use the pattern in the y values to determine the b. Looks like we are dividing by 2, but dividing by 2 is the same as multiplying by 1/2. So that common multiplier, that b value, is going to be the 1/2. And so I can say this is y equals A, which is 4, times b, which is 1/2, to the x power. All right, and the last one pretty clearly is linear. You absolutely can make a table of values here, but you may not need to. Right, we know definitely y equals mx plus b. And we can see the b value as the y-intercept, -4. And then we can calculate the slope by using our old rise over run. So if you just pick a couple of points, say that one and that one, I go up 2 and over 1. So my slope, rise over run, would be 2 over 1. Now, if you'd rather make a chart like this and identify the slope that way, you absolutely can do that, but it's not really necessary when you have a graph. So my equation is y equals m, which is 2 over 1, or just 2, times x, and then the b is -4. All right, so my hope is that you can identify linear versus exponential functions, certainly from a graph, but also from a table of values, and use those to come up with the actual equation for the function that you're looking at. All right, let's pursue a little bit further this idea about rate of change, absolute for linear functions, and relative for exponential functions. And we're going to go ahead and we're going to use the information here to write either a linear or exponential function to model each situation. So in example 2, we have a company with a profit of $2.7 million in the year 2010. It's been decreasing by $0.15 million per year. Write a function to model the situation, and then use it to predict the company's profit in 2022. All right, take a look at the rate of change statement. Decreasing by 0.15 million per year. That's an absolute rate of change, right? Relative rates of change are expressed as percents. This is not a percent. It's an actual value. It's an absolute rate of change. And for the absolute rate of change, I know I'm looking at a linear function. All right, so I'm writing an equation for profit. I'll call it P of t. And I know my slope. The slope's right here in the absolute rate of change, decreasing, so negative 0.15 times t plus the y-intercept. As long as we use 2010 as our starting year, then the 2.7 can be my y-intercept. So we'll assume t is years after 2010. All right, if I want to predict the profit in 2022, I'm going to say that, let's see, that would be 12 years after 2010, so I'd be looking at P of 12. And let's see what we have here. Looks like 0.9. And were these profits in millions? Yes, so we're looking at $0.9 million, or 900,000 if you prefer, as our profit in the year 2022. All right, compare that to some slightly different wording in example 3. Still a company whose profit was $2.7 million in the year 2010. This time it's been decreasing by 15% per year. Notice that as soon as we have a percent increase or decrease, we're now talking about a relative rate of change. The absolute rate of change tells you the exact amount it's increasing or decreasing. The relative rate of change describes the percent increase or decrease. So since we have a relative rate of change, we know we want an exponential function. So I'm going to go for P of t as a b to the t power. Once again, as long as we assume that t is years after 2010, the 2.7 million is going to be what we started with. So that'll be the a value here. And then I have to work just a little bit to get the b. If I think of that decreasing by 15% as a negative 15%, and then add back in the 100% that I started with, I now have 85% left. So my b value is 0.85. So unlike absolute rates of change, which basically you can just pick them out of the problem, relative rates of change, you always have to think a little bit about them, do a little bit of math to actually give you the value of the b in your equation. All right, and now our prediction for 2022. Again, that's 12 years after the starting year of 2010, so I want P of 12. And let's see what we get there. I get about 0.38, 0.384 million dollars. Right. We're going to look at a couple more similar to that. This time, though, the equations are going to be given, and we're just going to interpret them. So in example 4, number of employees at a particular company is given by this n of t, which is 140 times 1.12 to the t power, t being years after 2010. First of all, how many employees did the company have in 2010? This would be the starting amount. So I could either go right here and say, well, I know it's A. A is 140. Or alternatively, I could actually formally plug in t equals 0, 0 years after 2010. But of course, any number to the 0 power is 1. So I just have 140 times 1, or 140. Right? But if you recognize it and just can say, hey, that's the A value, the starting amount, that's perfectly fine. All right, it says describe the rate of change of this situation and be specific. I know that the rate of change is not the B value, but it's related to the B value. So I need B equals 1.12. I'd like to think of that as a percent, 112%. I have to subtract the 100% we started with, which says that the rate of change was actually 12%. The number of employees is increasing by 12% per year. All right, and then finally, how many employees will the company have in 2022? Again, since we're sticking with 2010 as our starting year, I would just need to plug in 12. So n of 12 is about 545 if I round to the nearest whole employee. Right. Once again, just for compare and contrast, a similar situation. We've got an equation giving us the number of employees at a particular company, but notice this time it's a linear function. So we start by saying how many employees did the company have in 2010? Since that's our starting year, that would be our y-intercept, or 140. Or alternatively, I could just take n of 0, right? 0 years after 2010. That would give me 12 times 0 plus 140, which still gives me 140. All right, describe the rate of change in this situation. In a linear function, it's an absolute rate of change. It's just going to be the slope. Since the slope is 12, that says that the number of employees increases by 12 every year. And notice how similar these statements are, and yet they mean something completely different, right? Here the number of employees increases not by 12 people, but by 12% every year. Here we have literally 12 more people every year. Constant relative growth rate, constant absolute growth rate. And then finally, we're going to predict how many employees in 2022. Remember, with the relative growth rate here, we had 545. Let's see what we get with the constant growth rate. We would want n of 12. So 12 times 12 plus 140 is going to give me 284. So you can definitely see different growth rates. We ended up with different predictions for 2022, depending on whether I had the relative growth, the exponential situation, or the absolute growth, the linear situation. All right, here in example 6, we have a table of values that shows us federal debt for various years in billions of dollars. And we would like to find a function to model this data and describe the rate of change in the situation, and then finally make a prediction for the year 2020. So I'm going to go ahead and let 1960 be my t equals 0 here. Almost got lulled into thinking we were every 10 years, but the pattern changed after a little while there. So there we go. There's our t values. And we really don't know at this stage whether this is going to be linear or exponential. So we need to graph these data points and see what we think. All right, and looking at that, that definitely looks like an exponential growth curve, not a linear function. So we're going to go ahead and model this with an exponential function. y1 tilde ab to the x1. Looks like a pretty good fit when I look over here, and my r squared is 0.99, so very happy with that. And they give us the a and the b value right there. So let's see, this is federal debt. We'll call it f of t. It would be 282.168 times 1.079. Go with 3 decimal places here, to the t power. All right, exponential function, so I'm expecting a relative or percent rate of change. I know that the b value is 1.079, which I'll interpret as 107.9%. Subtract the 100% that we started with, and the rate of change, or growth in this case, is 7.9%. That would be the increase in debt per year. All right, and then to predict for 2020, let's see, that would be 60 years after 1960. So if I calculate f of 60, see what we get here. I am getting 27,027 if I round to the nearest whole number. Everything in the table is whole numbers, so I'm just rounding my value here to the nearest whole number as well. 27027. And that would be in billions of dollars. Notice that that's about 27 trillion if you put the decimal point right in there. And that was the prediction for 2020. All right, one more here. This time we're given a world population table, and we want to find a function to model the data, and again, describe the rate of change and predict the world population, this time in 2025. So I'm going to go ahead and let my starting year here be 1950. And I got 20, 30, 40, 50, and 58. All right, there's our data points, and those definitely look a lot more like a straight line. Probably not perfect, but looks very close. So I'm going to go ahead and say we probably want a linear model here. So y1 tilde mx1 plus b. And there we go. Once again, an r squared of 0.99, which is really good. And there's the m and the b given to us. So I'm going to go with population, so I'll call it P of t, is 0.074 for m times t, plus the b value, 2.357. All right, this is an absolute rate of change since it's linear. So when I interpret my rate of change, I interpret that slope. M is 0.074. Population is increasing, since it's positive, by 0.074 billion people per year. And again, notice the difference. My rate of change is now absolute. It's the number of people per year, not the percent, like we had in the relative rate of change case. All right, and then finally, to make a prediction for 2025, that would be 75 years after 1950. So we'll go with P of 75. And I've got about 7.907, and that would be in billions. All right, that's probably a good place to stop. We're going to add another modeling type to compare and contrast next time, so I think this is a good place to stop here. That was that comparison then of linear and exponential models.